What is the relationship between a reaction mechanism and its elementary steps to the overall rate law of a chemical reaction? And one thing that will really help us to understand this is to understand the concept of a rate limiting step. Now, it's also called a rate determining step. These are interchangeable terms. They are synonyms. You may know it by this name, rate determining step. Personally, I like to use rate limiting step because it's fewer syllables, it's easier to say, and I'm a pretty lazy guy, so I call it the rate limiting step. But of course, it is up to you, whatever you want to call it, whether rate limiting or rate determining. Anyway, the rate limiting step is the slowest step in the mechanism of a chemical reaction. So generally speaking, chemical reactions that have mechanisms that occur by more than one step, usually one of those steps is going to be significantly slower than all of the other steps of that mechanism. And it's going to limit how fast the reaction can be, right? That's why we call it a rate limiting step. It's like a bottleneck, right? And it's also called the rate determining step because it determines what the chemical reaction rate is. The reaction can only proceed as fast as the rate limiting step of the reaction will allow. So in this example, right, the example that we've been talking about throughout this presentation with the NO2 and the Cl2 becoming ClNO2, the first step of the reaction, this one up here, is slow, significantly slower than the second step of the reaction. And so the first step of the reaction, in this case, is the rate limiting step. It determines the rate, or it limits the rate of the chemical reaction. So we can look at it graphically right here. So this is basically a diagram of the progress of the reaction from reactants all the way to products. The progress of the entire mechanism, right? So the reactants are up here. This is energy on the y-axis and the reaction progress on the x-axis. So you start out with your reactants, right? And for the first step of the chemical reaction, as in any step of a mechanism, it requires energy, right? It requires an activation barrier to overcome that barrier and become the product of that first step, right? And so this little valley here, this minimum right here, or local minimum I should say, this represents sort of the intermediates, right? But that's not necessarily the highest energy part or the most unstable part of the graph, right? It's these guys up here. These are the most unstable parts. These are called the transition states. So the transition states basically like, you know, the molecules of the reactants are kind of broken apart. You know, those bonds have kind of broken, and the bonds in the products have kind of formed, sort of like halfway in between. It's like the transition between the reactants and products, right? Or at least the reactants of one elementary step and the products of that elementary step. The transition state. So that's the energy maximum, or the local maximum of energy, right? Transition state, the most unstable species in the mechanism. So once step one is finished, you have this local minimum here that represents the intermediates, right? And then the second step of the reaction, step two, also has an activation barrier. Although notice that the activation barrier, right, the difference between this guy here and this guy up here, that activation barrier is lower than that of the first step, right? So this all goes back to the Arrhenius equation, where we understood mathematically that a higher activation barrier, according to the Arrhenius equation, results in a slower reaction rate. And so it makes sense in the context of this graph, right? Because a moment ago in the previous slide, we understood that the first step of this mechanism was the slow one, the rate limiting step, right? The one that determines the rate of the overall reaction. And so it's slower because it has the higher activation barrier. So you have step one, activation energy, you overcome that. You have step two, you have the activation energy, you overcome that, and then eventually you form the products. And notice that this particular chemical reaction is overall exothermic, meaning that the energy of the products is less than the energy of the reactants. So overall, this process releases energy. It's energetically downhill, so to speak. So if we look at this, so we talked about this, we're continuing our discussion on this two-step mechanism, right? And we just saw a moment ago the sort of humps, the camel humps, as I call them, the activation barriers, and how the activation barrier for the slower step is higher than the activation barrier for the faster step, right? And so each one of these elementary steps, step 1 and 2, they have their own characteristic rate constant. And they have their own characteristic rate constant because, again, each of them have their own characteristic activation energies. The activation energy, the first step happens to be larger than that of the second step. So we would expect K1, right, this rate constant for the first step, to be smaller than the rate constant for this reaction here, this step here, K2. So if we wanted to write a rate law for this chemical reaction, right? So the rate law of a chemical reaction is simply going to be the rate law of the rate limiting step. Let me repeat that because it's not written on the slide, so I just want to make sure we all understand that. The rate law of the overall reaction is going to be the rate law for the rate limiting step, for the slowest step, right? Because it is that slowest step that determines the overall rate for the chemical reaction. So the rate for the reaction is going to be the rate of your rate limiting step. In this case, it happens to be the first step. That's the slowest step. So if we wanted to write the rate law of this reaction predicted by this mechanism, it would look like this. Rate equals K times the concentration of NO2 times the concentration of Cl2. Why is that? Well, because a moment ago we were talking about molecularity, right? This step represents a bimolecular process where we have one NO2 molecule slamming into one Cl2 molecule, right? And when you have a bimolecular process of two different chemical species, the rate will be the rate constant times the concentration of one of those species times the concentration of the other species. And so far in this discussion, we've been talking about how reaction mechanisms are never proven, right? They are only validated, okay? Because again, you can't interview the molecules to figure out where they've been, right? And so keeping that in mind, there are two conditions that must be met in order for a reaction mechanism to be considered valid. If either of these two or both of these two conditions are not met, then the mechanism is invalid. So what are those two conditions? Well, the first condition is something that we kind of went over previously, which is the sum of the elementary steps must be equal to the overall chemical reaction, right? The equations for the individual steps of the reaction, when you add them together, they must equate to the overall balanced chemical equation for the reaction. And the other condition that must be met in order for a reaction mechanism to be considered valid is that the rate law predicted by the mechanism must be consistent with the experimentally observed rate law. So that's kind of a big blurb of words, so allow me to explain. So again, the way that kinetics works, or the way that kinetics is used to elucidate or validate reaction mechanisms, is it's done experimentally, right? And experimentally, you can measure the concentrations of reactants, you can measure the concentration of products, but you cannot measure the concentrations of intermediates. And remember, the intermediates are those things that get produced in one step and then consumed in another, right? So when you're performing a kinetic experiment, since you can't measure the concentrations of intermediates because as soon as they're produced, they're consumed right away, experimentally, the only type of rate law that you can determine, right, the only type of rate law that you can write out, rate equals K times whatever, has to be in terms of concentrations of reactants and or products. It cannot be expressed in terms of concentrations of intermediates. And so this last little blurb down here says that there are no intermediates allowed in the rate law. So again, the rate law being predicted by the mechanism being consistent with the experimentally observed rate law, basically that just means that you can't have intermediates in the rate law. And so we're going to see how this works when we do a couple of examples. So going back to the reaction that we've been discussing this whole time, right? So we can see here, we went over this a moment ago in a previous slide, but I think it's worth revisiting at this point. So one of these two conditions we can see is clearly satisfied. So this mechanism, this two-step mechanism, satisfies the condition that the sum of the individual steps must be equal to the overall chemical equation, right? So that condition is met. We don't have to worry about that. Now the second condition, right, which is that the the rate law predicted by the mechanism must be consistent with the experimentally observed rate law. In other words, no intermediates in the rate law. Well, that condition is also met. Why? Well, because we can see that the rate law that we got by the mechanism, right? And again, the way that we arrived at this rate law up here, rate equals K times concentration of NO2 times concentration of Cl2, the way that we arrived at that rate law is by understanding that the first step of the reaction is the slow one, the rate limiting step. And so the rate law of the overall reaction is simply the rate law of the rate limiting step. And so this is how we arrive at this equation up here. And it is consistent with an experimentally observed rate law. Why? Because there are no intermediates, right? NO2, if we look down at the overall chemical equation, NO2, that's a reactant, that's not an intermediate. Cl2, also a reactant, that's not an intermediate. So our rate law does not contain any intermediates, which means that it is consistent with any experimentally observed rate law, which means that it satisfies the second condition. Finally, which means that this mechanism here is indeed a valid mechanism for this chemical reaction. So far, the mechanism that we looked at, right, we were able to arrive at a rate law. Okay, we were able to arrive at a rate law for a mechanism with a slow initial step, with a slow first step. And that was fairly easy, right? Because we had the rate is equal to concentration of one reactant times concentration of another reactant. Because the first step was our rate limiting step, we didn't have to worry about any intermediates appearing in our rate law equation, right? Now, what if we had a mechanism in which the first step was fast, right? And the rate limiting step appeared somewhere else within the mechanism, either the second or third or fourth or whatever step. So if the first step is fast and the rate limiting step is some other step, how would we determine the rate law predicted by the mechanism for that type of mechanism? So I'm going to walk through this problem here. So it basically says, consider the following reaction. We have 2H2 plus 2NO yields 2H2O plus N2. And it says that the experimentally determined rate law is rate equals K times concentration of H2 times concentration of NO2 squared. And it says to show that the following proposed mechanism is consistent with the experimentally determined rate law. Now, I really like problems like these. I really do. And the reason why I like problems like these is because you can't bullshit your way out of it. You can't cheat to the answer, because this is like you have to show your work, type of problem. So let's unpack what's going on with this mechanism. So if we look at this first step, now we got these funky looking arrows right here. Does anybody in the chat happen to know what these funky looking arrows mean? Okay, so we have a couple messages in the chat that I'm seeing now. Crazy Wolf says equilibrium. Victoria says equilibrium. You guys are both correct. If I had a gold star or a piece of candy to give you, I would. So yes, this represents an equilibrium. So basically what's happening here, right, is that the first step is fast. The second step is slow. Now, because the first step is fast and the second step is slow, the product of the first step sort of builds up, and it doesn't react very quickly because the second step is so slow. And so you have the product of that first step building up and building up and building up and building up to the point where the substances on the right-hand side of this equation, the products, actually react with one another. In this case, this decomposes to form the reactants. So you have both a forward reaction taking place and a reverse reaction taking place simultaneously. It's called a dynamic equilibrium. Both of these processes, the forward reaction where you have two nitric oxide molecules reacting to form N2O2, that process is happening at the same time the N2O2 is breaking down into two nitric oxides, right? Dynamic process. And what these two arrows mean is that they're in equilibrium. And what equilibrium means is that the rates of the forward and reverse reactions are the same. In other words, this process, the forward process where the NO is becoming N2O2, that is occurring at the same speed, the same rate as the opposite, N2O2 becoming NO. And we're denoting the rate constants of these two processes. The forward rate constant we're calling K1, and the rate constant associated with the reverse reaction we're calling K minus 1. So hopefully I've explained the context well enough. If anything is unclear, I would certainly appreciate you letting me know, and we will go ahead and move forward. Okay, so the first step is, like I said, N2 becoming N2O2, but again, the products build up to the point where they're in equilibrium, right? Forward and reverse reactions happening at the same time. The rates of those reactions are the same. In the second step, you have H2 reacting with N2O2 to produce H2O plus N2O. That's the slow step. That's the rate limiting step. So that's the step that determines the overall rate of the chemical reaction. And then finally, in the third step, we have N2O plus H2 yields N2 plus H2O. And it looks like my N2 is missing a state of matter. Shame on me. I should have put a little G there. I know it's really not important for the purpose of understanding mechanisms, but I don't know. I'm a perfectionist, which is why I believe I was attracted to chemistry in the first place. Okay, so again, the goal here is to show our work. We want to show that this proposed mechanism is consistent with the experimentally determined rate law. So how do we do that? Well, okay, the first thing that we want to do in tackling a problem like this is to see whether or not the first condition, right? Remember, there are two conditions that must be satisfied in order for a mechanism to be considered valid. The first one is that the steps of the reaction must equate to the overall equation, right? All the steps, all the sum of all of these elementary steps must be equal to the overall reaction, right? And so if we start looking at what we can add to, if we add these three equations together and look at what we can cancel out, well, it looks like there's an N2O here and an N2O here. What else? Are there any other intermediates that we can cancel out? So Crazy Wolf asks, would N2O be the intermediate? Yes, it is. It is an intermediate. But we also have another intermediate. Can you find it? Yeah, it's the N2O2, right? It's produced in the first step and it's consumed in the second step, right? There's no N2O2 in the overall reaction equation. So it looks like to me, okay, so for the reactants of the overall equation, we have two H2s. There's an H2 there and an H2 there. We have two NOs, right? So we have two NOs right there. And then on the product side, we have two H2Os. So there's one H2O there, one H2O there. And then we have N2. And again, shame on me for not putting the G for gas right there. Okay, so we have just successfully determined that the first condition is satisfied. The sum of the individual steps do indeed equate to the overall reaction equation. So the next step, right, is that the rate law predicted by the mechanism must be consistent with the experimentally observed rate law. Now, in this case, we know what the experimentally the experimentally observed rate law is, right? Sorry, I'm a newbie at this. I'm trying to highlight something, and this is proving more difficult than I imagined. Okay. So this is the experimentally observed rate law, right? Rate equals K times the concentration of H2 times the concentration of NO2 squared. So we have to show that the rate law predicted by the mechanism is consistent with the experimentally observed rate law. And so how do we do that? How do we do that? Well, recall that the rate law for a chemical reaction is simply the rate law for the rate limiting step of the chemical reaction. And the rate limiting step, of course, is this one right here, the slow one, right? And so the rate is going to be equal to K, in this case K2, right, times the concentration of H2 times the concentration of N2O2, right? Got a message from Peace and Love, says, hey, how are you doing? Or, hi, how are you doing? I'm doing very well. How are you? And thank you very much for dropping into my stream. I wholeheartedly appreciate it. Okay, so the rate of the reaction is the rate law of the reaction is the rate law of the rate limiting step, right? And so the rate law of the limiting step looks like this, where we have rate equals K2 times concentration of A2 or H2 times concentration of N2O2. And I hope we're all following along. If not, please let me know, and I can back up and re-explain something. I don't always do a great job of explaining. In fact, I very rarely do a great job of explaining. So, okay, so this must be the rate law of our reaction. However, this rate law isn't going to work because there's no way that this rate law predicted by the mechanism can be consistent with the experimentally observed rate law. And the reason why is because N2O2, right, this guy over here, is an intermediate. And the rate law for an overall reaction can never have an intermediate in it, right? The reactants are H2 and NO. They're not N2O2, right? So this is a problem, right? Our rate law has an intermediate, but our rate law can't have an intermediate. How do we solve this problem? And the answer to how we solve this problem is that we can express the concentration of the intermediate in terms of the concentrations of other species, reactants or products, usually reactants, right? And the way that we can do that is by understanding a few things about chemical equilibrium. And so if we look at this first step, right, earlier, we said that this is a dynamic equilibrium. Both the forward and the reverse reactions are happening at the same time and at the same rate. That's what equilibrium means. So the rate of, and I'll just say the rate of the forward reaction, rate sub F, is equal to the rate of the reverse reaction, which I'll call rate sub R. And again, this is all step one, right? So the equilibrium process that is characterized by step one, this equation, rate forward reaction equals rate reverse reaction, this equation applies to step one, the fast equilibrium step, right? So if we set those rates equal to one another, well, and if we express those rates in terms of rate law, well, the rate of the forward reaction is going to be K1 times the concentration of NO squared. Why is it NO squared and not just NO? It's because of this too. We have two NO molecules. This is a bimolecular process. Two of those molecules colliding together, right? So that's the rate of the forward reaction, and that must be equal to the rate of the reverse reaction, which was going to be, it's going to be K minus 1 times the concentration of N2O2. And that doesn't have anything squared or anything because that's a unimolecular process with just one molecule in it. Sorry, I'm going to backtrack just a little bit here. So the rate of the forward reaction is equal to the rate of the reverse reaction. So these are the expressions for the rate laws of those reactions. And so if we solve for N2O2, right, if we solve for concentration of N2O2, well, in this equation, we can simply divide both sides of it by K minus 1, right? And so what we end up with is N2O2, or the concentration of N2O2, equals K1 over K minus 1 times the concentration of NO squared. Okay? So again, the reason why we're doing all this is because the rate law predicted by the mechanism has to be consistent with the experimentally observed rate law, And in order to be consistent with the experimentally observed rate law, it cannot contain any intermediates. The rate law of our rate limiting step has an intermediate in it, and so we need to express that intermediate in terms of reactants. And the way that we do that is by understanding this equilibrium relationship between the rate of the forward and the rate of the reverse reactions. So we just found an expression for the concentration of N2O2, right? So that's this thing right here. So if we take that, I'm going to try to get fancy here. If you guys, if you guys will bear with me, I'm going to try to get fancy here. Okay, so here we go. All right, so I'm going to lasso this N2O2, right? I'm going to lasso that, and I'm going to drag it away, and I'm going to take this expression, which is equivalent to the concentration of N2O2, and I'm going to drag it in and substitute it right there. Look at that. Look at that. I'm slowly learning. Might have taken 7 live streams to figure this out, but hey, better late than never, right? Okay, so we end up at this sort of long-winded equation over here, and I'm going to clean this up a little bit. I'm just going to say that the rate is equal to K1, K2 over K minus 1 times the concentration of H2 times the concentration of NO squared. Yeah, by the way, this is, I just realized this is a typo. This should be NO. This shouldn't be NO2. There's no NO2 anywhere in here. So, yeah, I messed that one up. If anybody caught me on that, yeah, I apologize for the confusion. I really do. So, let me see if I can fix that. It doesn't look like I can, but okay. You guys understand that this is a typo over here. This should say NO. It should not say NO2, right? So just keep that in mind, and I do apologize for the mistake. Okay. So this is the equation that we have right here, where we have, whoops, go back to the pen. So rate equals K1, K2 over K minus 1 times concentration of H2 times concentration of NO squared. Well, this K1, K2 over K minus 1, that's kind of a long-winded way to express a constant. Because if you think about it, a constant times a constant divided by another constant is a constant, right? And so we can simplify this down, and I'll do it in blue here. Actually, I'll do it in green. We can simplify this down to rate is equal to K, we'll just call it K because, again, a constant times a constant divided by a constant is a constant, times the concentration of H2 times the concentration of NO squared. So, again, this problem wasn't really about like finding an answer so much. It was about showing your work. It was about showing your knowledge, that you're familiar with the fact that the rate law of a reaction is the rate law of the rate limiting step of the reaction, and if that rate limiting step has any intermediates in it, which is often the case when the first step of the reaction is fast and the second or third step or subsequent step is slow. If the rate limiting step, if the rate law has intermediates in it, you must find a way to express the concentration of those intermediates in terms of reactants and or products, usually reactants. Okay. Hey, hope you enjoyed the video. If you'd like to watch the full video from which this clip was taken, click the box over there on the left. And if you'd like to watch my entire chemical kinetics playlist, click the box on the right. Thank you very much for watching, and take care.